with Clara on an ongoing effort in the computational linguistics department called the AIDA project, which concerns narrative coherence in a graphical setting. So the central motivation here is that reports covering conflict events are often difficult to disentangle. If a plane is shot down, for instance, there might be numerous reports describing the event, each differing in their characterization of who the attacker was, what weapon was used, where the attack occurred, etc. The AIDA project is intended to push systems capable of discerning between conflicting narratives. Our specific task is the following. Given a graph which represents a mixture of different narratives, and given a subgraph which represents the beginning of one of those narratives, our goal is to expand the narrative by adding other pieces of the graph which extend that initial seed in meaningful ways. Our graph structure is composed of two core components. EREs are nodes in the graph which represent events, relations, and entities, and statements describe roles entities take in events and relations. We use a synthetic corpus of mixtures of Wikipedia articles covering conflict events that we developed earlier this year. We first cover our previous fully supervised approach and then move on to discuss our RL extensions. We use a graph convolutional network, or GCN, to develop embeddings for nodes in our graph and propagate information throughout the graph structure. Once we've induced embeddings for nodes in our graph, we allow candidates, or statements we are considering adding to the narrative, to attend to each part of the existing narrative. We use a standard attention mechanism to develop context vectors for each candidate, and we then feed each candidate along with its context vector into a final network to produce a probability distribution over candidate statements. Our supervised model admits the candidate statement with the highest probability. Now, we move on to our RL extension.
The task of our agent is to expand an initial query set. Our statement information comprises a list of GCN embeddings that is our query set and possible actions that represent by addition of each candidate statement at a given time step. Our reward signal is a simple +1, -2 based on whether the emitted statement belongs to the target graph. Lastly, the motivation behind using RL here is that it might also allow us to fold in desired graph structural properties through a nuanced reward function. Most policy gradient methods perform one gradient per data sample. PPO implements multiple epochs of mini-batch updates. A policy gradient method computes an estimator of the policy gradient to calculate stochastic gradient ascent. The algorithm alternates between sampling and optimization. Without constraints, maximizing the policy iteration lot leads to large policy updates. The objection function we use has two terms. The first term is the CPI loss. The second term modifies the objective by clipping the probability ratio and thus reducing the size of the update. The PPO algorithm iterates for each time step over each actor, running the old policy to generate an episode trajectory. Afterward, we compute the advantage for each time step. Finally, the algorithm optimizes the loss with respect to the network weights. Most techniques for computing variance-reduced advantage function estimators use a learned state value function. An advantage function is nothing but the difference between the Q value for a given state action pair and a value function of the state. PPO uses a loss function that combined with policy loss and value function error. We do not add an entropy bonus, even though you can.
So we conduct two sets of experiments. To make the task easier for the learner, we first pre-train our actor network on a classical supervised learning task on a subset of our training data that we have applied before. For one set of experiments, we then subsequently train the final layer of our actor and the critic network on the remainder of the data. For the other set of experiments, the dual experiments, we freeze only the GCN weights and train two separate attention networks, one for the actor and one for the critic. Our learning curves for the two settings are displayed here. We see that no statistically significant performance gains really appear to be made from the initial starting point. Here we see our loss objectives for each setting. Our loss objectives unfortunately explode for cases in which we clip both the value function and actor networks. This will require future investigation. Lastly, our two principal difficulties have been the high dimensionality of word vectors. Here they're around of hidden size 300, and the lack of a true quote-unquote ground truth, which limits the expressivity of our reward function. So in the future, we hope to further tune our reward signal. The current one seems a little insufficient, and we also hope to later encode those desired graph properties into our reward signal.